Klaus-Peter Schnorr invented his signature scheme in 1989. It was simpler, more efficient, and more elegant than ECDSA. So why did Satoshi not use it? Because Schnorr patented it. The patent did not expire until February 2008, just months before the Bitcoin white paper. By the time Bitcoin launched, every standard library used ECDSA. It took 12 years for Schnorr to arrive in Bitcoin through the Taproot upgrade in November 2021. Schnorr signing has 5 steps. Step 1. Generate a deterministic nonce key by hashing auxiliary randomness, the private key, and the message together. Step 2. Compute the nonce point r equals k times g. If the y-coordinate of r is odd, negate k so that r has an even y-coordinate. Step 3. Compute the challenge e by hashing r, the public key q, and the message together. Step 4. Compute s equals k plus e times d, modulo n. Step 5. The signature is the pair r, sr is encoded as its x-coordinate alone, 32 bytes, and s is 32 bytes. The total signature is 64 bytes, the same size as ECDSA. Notice the hash functions use tagged hashing. Each hash is prefixed with a domain-specific tag, like BIP0340 challenge or BIP0340 nonce. This domain separation ensures that a hash computed for nonce generation can never collide with a hash computed for challenges, even if the inputs overlap. Schnorr verification is remarkable. Compute the challenge E by hashing R, Q, and the message. Then check a single equation, S times G equals R plus E times Q. That is the entire verification algorithm. One equation, 3 terms. Why does this equation hold? Start with the signing formula, S equals K plus ED. Multiply both sides by G. On the left side, S times G. On the right side, K plus ED times G. Distribute, KG plus ADG, but KG is R and DG is Q, so R plus EQ. The two sides match. Verification accepts. Compare this to the ECDSA correctness proof from episode 10, which required computing modular inverses and tracking substitutions through multiple steps. Schnorr needs 3 lines. This simplicity is not merely aesthetic. It makes security proofs cleaner, implementations simpler, and bugs less likely. Side by side, the contrast is stark. ECDSA signing requires a modular inverse, S equals K inverse times Z plus RD. Schnorr signing is purely additive, S equals K plus ED. ECDSA verification needs 2 scalar multiplications and a coordinate check. Schnorr verification is one equation. ECDSA is malleable. Both R, S, and R, n minus S, are valid. Schnorr is canonical by construction, and critically, Schnorr supports signature aggregation while ECDSA does not. The key difference is linearity. ECDSA uses the formula S equals K inverse times Z plus RD. The modular inverse makes this nonlinear. You cannot simply add 2 ECDSA signatures together. Schnorr uses S equals K plus ED. This is a linear equation. If 2 signers each produce S1 equals K1 plus ED1 and S2 equals K2 plus AD2, the sum S1 plus S2 corresponds to a valid signature on the combined key. This linearity is what makes multi-signatures possible. It is the mathematical foundation of MUSIG and Taproot. Schnorr also enables batch verification. When a Bitcoin node receives a block with hundreds of signatures, instead of verifying each one individually, it can combine them into a single equation using random weights. The result? Verifying M signatures takes roughly the time of M over 2 plus 1 individual verifications, approximately a 2 times speedup for large batches. BIP 340, co-authored by Peter Wile, Jonas Nick, and Tim Ruffing, specifies several Bitcoin-specific design choices. Public keys use only the X-coordinate, 32 bytes instead of 33. All hash functions use tagged hashing for domain separation, and signatures are canonical by construction, eliminating the malleability issues that plagued ECDSA. Before Taproot, a multi-signature transaction was visibly different from a regular payment on the blockchain. With Schnorr and Taproot, a cooperative multi-signature spend looks identical to a single signer spend, 1 public key, 1 signature. This is a profound privacy improvement. When the common case is indistinguishable from a simple payment, blockchain analysis becomes much harder. For Steiner, true understanding results in simplicity, not because the subject is trivial, but because the mind has penetrated to its essence. ECDSA requires computing inverses, tracking two scalar multiplications, and checking an x-coordinate. Schnorr requires checking SG equals R plus EQ, one equation, three terms. The simpler formula is not a shortcut, it is deeper seeing. Schnorr signatures are linear. This linearity enables something ECDSA could never do, multiple signers combining their signatures into one. Episode 12 explores MUSIG, the multi-signature protocol that makes Taproot possible. Subscribe for Episode 12, MUSIG and Multi-Signatures. Companion materials for this episode are in the description. See you in Episode 12.